Welcome to ENG-001. We're going to be doing some MasterCAM programming on this part here. So follow along. You can see right here I have myself my design file. I have my drawing opened up. And I also have my assembly for reference for the duration of this tutorial. As always, I kind of like to overview the part just to see what's going on. As normal, we can normally pull the dimensions off the part as we program, but many times when we export our part, we'll see when we input this into MasterCAM that the whole definitions will not go with it. So when you export it, Fusion 360 likes to not, let's say if it's a /20 thread, it might export the hole size of 0.201 hole, which would be the tap drill size for certain /20 holes. So just want to be careful. That's why you always want to look at your drawing just to see what we got going on for some of our holes. So I can see on the top right here, we have two 1032 tapped holes. So that's good to know. You can see the depth as well. We need to make sure we give our customer at least 0.375 worth of threads. We can see we have two /20 threads with a depth of 0.5 inches. Again, making sure that we're going to get them 0.5 worth of threads. So that we'll talk about that, how we're going to push the drill a little bit deeper just to make sure we get the full amount of threads for our customer. And lastly, I see right here, we have a 0.2495 hole, two places, plus 2 thou, minus 0. That's an interesting one here. Okay, so that is a pretty tight tolerance hole, so we're going to keep that in mind. We might have to take a different approach to that, and I can actually see on the right side, I see ream to suit. So I can start thinking about how I'm going to make this. But first off, let's get this part into our MasterCAM. So first thing I'm going to do, actually, I don't think I've exported this part yet, so I'm just going to export my part as a step file. And I'm going to save it as left hand, yes, export. It looks like I did, but that's okay. I can move over to my MasterCAM file, file, open, computer. I'm going to go to my 436 engine curriculum on ENG-001 and click all files, which will then allow me to see my step file that I created. So as always, let's set up our machine. I could also see I am in millimeters once again. So let me go to my file, configuration. Let's go to inches, hit OK, and hit OK. Now I should, because the second time I've done this, I should really change my default setting so that I always open parts in inches because that is typically what I use. I'm going to right click and clear my colors to get rid of that. I am also going to go to view and turn off my noms for now, because again, a bit misleading having them on right now. We'll set our plane ourselves. So let's go and set up our machine. We're going to go mill default. We're going to open up our properties. And right off the bat, we'll go to our files. Let's give this our name. So I'm going to type in ENG-001, and we can call this engine block left hand, which is the name of this part. Again, if you want to add any specific comments, you can. Everything else should be good. We're going to go to our, oh, actually, where's my program number? Program number, this is what I want here. Under program number, I'm going to want to change this to a specific number. Perhaps we can do 43601. We'll call it because it's our first part of our 436 curriculum. I don't know if I named my third part, but that's okay. We should always change it. It's always good to have a number. That way when you upload it, it has its own defining characteristics that won't overwrite it. So there's no way that really the odds are very low that in our CNC we have a part already numbered that. It is good to come up with a numbering system for your shop if you ever do own a shop. That way you can stay organized. Maybe you'll have certain codes for clients on a 1 to 1,000, and then you could just label their parts from 1 to 100, let's say. So I'm going to select my model from selection, and as you can see, I did that. So I selected my part. I'm I am going to keep everything else the same. I do not have my stock in here yet, so I'm going to come back to this menu later on when we want to simulate. I do not have any work holding here, so we can skip by this and we can skip by our tool and simulation setup as well. So I'm going to hit OK. So we need to look into setting up our stock. Before we do that, we should create a new level, and we're going to call this level our stock. Oh, make sure this is checked off, so any new geometry created is input into our stock level. I'm going to go wireframe, and we're going to create a bounding box around our part. Again, guys, as we go through this, I want you to keep in mind that this is the first time I'm going through this part. So everything you see here, I really haven't planned out. I want you guys to see the planning process as I use it. So this bounding box will give me a good head start to what my stock could look like. I already have an idea of how I'm going to go for my operations. I can count that we will have, well, 1, 2, 3 operations on this part, I believe. This will be a 3 operation part, and we'll talk about why that is in a bit. But based off this, I can see my X, my Y, and my Z. I think that's already correct, but we could double check to make sure that everything's right. Yeah, our axis is already in the right direction. So we don't got to worry about that. We will set the origin to the top middle. So I could see that we have, okay, this is interesting. We have 2" 0.375 in the X, we have Y 0.9375, and we have a Z of 1.4. Okay, so typically you're going to look at your 2 smallest dimensions for the cross section of stock that you will order. We typically want at least, I know, you hear me say some different things, but I could tell we're going to cut it close on this part. So in our Y, we just even 20 thou at least on each side would be nice. In our Z, we want as much as possible, and in our X, I typically like to have at least 50 thou on each side, just because the X is the one that's the easiest to mess up as you put the stock in your machine. It's easy to not line it up in the X correctly, whereas the Y, it's always going to bump up against the back face of your jaw, and your Z is always going to bump onto your parallel. Um, so um, welcome to ENG-001. We're going to be doing some MasterCAM programming on this part here. So follow along. You can see right here, I have myself my design file. I have my drawing opened up. And I also have my assembly for reference for the duration of this tutorial. As always, I kind of like to overview the part just to see what's going on. As normal, we can normally pull the dimensions off the part as we program, but many times when we export our part, we'll see when we input this into MasterCAM that the whole definitions will not go with it. So when you export it, Fusion 360 likes to not, let's say if it's a /20 thread, it might export the hole size of 0.201 hole, which would be the tap drill size for certain /20 holes. So just want to be careful. That's why you always want to look at your drawing just to see what we got going on for some of our holes. So I can see on the top right here, we have 2 1032 tapped holes. So that's good to know. You can see the depth as well. We need to make sure we give our customer at least 0.375 worth of threads. We can see we have two /20 threads with a depth of 0.5 inches. Again, making sure that we're going to get them 0.5 worth of threads. So that we'll talk about that, how we're going to push the drill a little bit deeper just to make sure we get the full amount of threads for our customer. And lastly, I see right here, we have a 0.2495 hole, 2 places, plus 2 thou, minus 0. That's an interesting one here. Okay, so that is a pretty tight tolerance hole, so we're going to keep that in mind. We might have to take a different approach to that, and I can actually see on the right side, I see ream to suit. So I can start thinking about how I'm going to make this. But first off, let's get this part into our MasterCAM. So first thing I'm going to do, actually, I don't think I've exported this part yet, so I'm just going to export my part as a step file. and I'm going to save it as left hand. Yes. Export. It looks like I did, but that's okay. I can move over to my MasterCAM file. File, open, computer. I'm going to go to my 436 engine curriculum on ENG-001 and click all files, which will then allow me to see my step file that I created. So as always, let's set up our machine. I could also see I am in millimeters once again. So let me go to my file, configuration. Let's go to inches, hit OK, and hit OK. Now I should, because the second time I've done this, I should really change my default setting so that I always open parts in inches, because that is typically what I use. I'm going to right click and clear my colors to get rid of that. I am also going to go to view and turn off my noms for now, because again, a bit misleading having them on right now. We'll set our plane ourselves. So let's go and set up our machine. We're going to go mill default. We're going to open up our properties, and right off the bat, we'll go to our files. Let's give this our name. So I'm going to type in ENG-001, and we can call this engine block left hand, which is the name of this part. Again, if you want to add any specific comments, you can. Everything else should be good. We're going to go to our, oh, actually, where's my program number? Program number, this is what I want here. Under program number, I'm going to want to change this to a specific number. Perhaps we can do 43601. We'll call it, because it's our first part of our 436 curriculum. I don't know if I named my third part, but that's okay. We should always change it. It's always good to have a number. That way when you upload it, it has its own defining characteristics that won't overwrite it. So there's no way that really the odds are very low that in our CNC we have a part already numbered that. It is good to come up with a numbering system for your shop if you ever do own a shop. That way you can stay organized. Maybe you'll have certain codes for clients on a 1 to 1,000, and then you could just label their parts from 1 to 100, let's say. So I'm going to select my model from selection, and as you can see, I did that. So I selected my part. I am going to keep everything else the same. I do not have my stock in here yet, so I'm going to come back to this menu later on when we want to simulate. I do not have any work holding here, so we can skip by this, and we can skip by our tool and simulation setup as well. So I'm going to hit OK. So we need to look into setting up our stock. Before we do that, we should create a new level, and we're going to call this level our stock. Oh. Make sure this is checked off, so any new geometry created is input into our stock level. I'm going to go wireframe, and we're going to create a bounding box around our part. Again, guys, as we go through this, I want you to keep in mind that this is the first time I'm going through this part. So everything you see here, I really haven't planned out. I want you guys to see the planning process as I use it. So this bounding box will give me a good head start to what my stock could look like. I already have an idea of how I'm going to go for my operations. I can count that we will have, well, 1, 2, 3 operations on this part, I believe. This will be a 3 operation part, and we'll talk about why that is in a bit. But based off this, I can see my X, my Y, and my Z. I think that's already correct, but we could double check to make sure that everything's right. Yeah, our axis is already in the right direction, so we don't got to worry about that. We will set the origin to the top middle. So I could see that we have, okay, this is interesting. We have 2 inch 0.375 in the X, we have Y 0.9375, and we have a Z of 1.4. Okay, so typically you're going to look at your 2 smallest dimensions for the cross section of stock that you will order. We typically want at least, I know, you hear me say some different things, but I could tell we're going to cut it close on this part. So in our Y, we just even 20 thou at least on each side would be nice. In our Z, we want as much as possible. And in our X, I typically like to have at least 50 thou on each side, just because the X is the one that's the easiest to mess up as you put the stock in your machine. It's easy to not line it up in the X correctly, whereas the Y, it's always going to bump up against the back face of your jaw, and your Z is always going to bump onto your parallel. So right off the bat, based on these numbers I see, I think that 1x2 inch aluminum will work for us. I could see if we can bump up our Y to 1 inch. That would add a little bit of material on each side. Not a lot, but it's okay in the Y because, again, our vise is pretty accurate. There's no way our part's going to go in that vise on a line, so even just a little bit of material on each side is nice. In our Z, I believe I'm going to set my 2-inch value. Well, obviously I have to set this one as my 2 inch because my X is greater than 2 inches. So I'm going to set this as 2 inches. And my X, I at least want to add 50 thou to each side, so at least 0.1 to that number, which will give me 2.475. So let's just increase this a little bit more and get us to 2.5 inches, just a nice round number, because that is what the person cutting the stock is going to have to cut it to. So by setting it to a nice even number, a nice fraction, or a nice tenth of a decimal, it's very easy for the operator of the bandsaw to cut this exactly to size without having to do with just using regular rulers and measuring tapes. So this looks good. Now, as you can see, I've already kind of added the stock how I've planned this. I'm adding the stock to the bottom of this part right here. And this is just one of the ways we could have went about it, but based on the way my stock is, I like this orientation. It leaves us a little bit of stock on the bottom to hold into our vise. If you guys are wondering how I plan on machining this, I see this top side being op 1, where we will face our part, we will spot drill, and tap these 2 holes. Now, because we have the carrier on the bottom side of the part, we will want to get rid of that. And typically you want to get rid of the carrier in op 2 because the carrier is this weird piece of stock that would just get in the way if you tried to machine, let's say, this side next. So we're going to flip over the part and machine from this side and just face it down to 0. As you can see, we still have nice square features from our part on the inside on each side to hold into our jaws. And then lastly, we'll have all this will be gone and we can flip this face up like so and machine this face and the features you see here. Now, the reason why I'm holding this straight up is because one of the main reasons why I'm going about this way is right off the bat, I want to do the profile of the part. I always like to do the outside profile of the part typically in my first operation if possible. Now, if I flipped it on this side, I could have, machined the outside profile of the part, but I wouldn't have been able to machine the radius in these corners right here. They would be inaccessible from this side of the part. If I hold my part straight up like this, I can machine these radiuses and the entire profile all at once. So in my case, in my knowledge, I believe that this is a really good side to start on. Because again, if you start on this side and then you had to flip to this side to machine op 2, you really couldn't get this radius into your part. There are tools, corner rounding tools that can technically do that from the top like this, get this round in there. But the best method is definitely just to use an end mill and come at it from the top like this and just do a contour around our part. So this is how I'm going to hold on to my part. I have a little bit of stock on each side, which is really good, and lots of stock on the bottom. A little bit extra, but a little bit extra is not always the worst thing in the world because that just means really less chance of crashing into our vise. So I'm going to make sure that solids is checked off here, and I'm going to hit OK. What I'm going to do now is I'm just going to hit my wireframe view, and I'm just going to move my part 20 thou below the surface just so we have that 20 thou stock on top. So I'm going to go to my transform tab. I'm going to click on translate, and I'm going to click on my part on the inside here. And I'm just going to grab the Z axis and type minus 0.02, enter, enter again, and just make sure I check off move under my translate feature. So my part moves instead of being creates a copy. And then I'm just going to hit my green check mark. Okay, I like this. Again, we have this purple color, so I can just right click and say clear colors to get rid of that. I'm going to go back to my solids, and now that we do have our stock set up, let's go back into our stock setup and or at least I shouldn't say stock setup, but we at least have a model of our stock now. We can add our stock. So I'm going to go add from selection, and I'm going to click on this stock model or the stock so that our program knows what is the stock for our simulation. Now, this is where I take a little bit of a turn based on where Titans of CNC came from. As you saw, I moved my part 20 thou below the surface. This will allow me to face my part, but what I'm going to do is I'm going to face my part and then create my stock model, right? So in this case, because we make the stock model after the facing, it'll actually notice that the 20 thou has been faced away. So when the stock model is created, it will create the stock model without that 20 thou. So the benefit of that being is we see what our stock actually looks like. We don't just have to pretend there's 20 thou on the top of our part, but we can but we still get the proper tool path when it comes to our OptiRough when we do the 3D machining, okay? The trick is, and really the rule is, when you make your stock model, you should just make your stock model right about before you do any 3D tool paths, because a stock model is really meant for those 3D tool paths. They are also good for uh, every once in a while creating some stock models to see what your stock looks like as a reference. So other than that, we're going to kind of follow the basics of what Titans of CNC did. So we're going to start with a facing tool path. Okay. I'm going to click my top surface of my part. You can see some of these selections of my part are coming through. I want to make sure not to select that. I just want the outside of my stock, just like so. Which is why it's nice to have this stock in our levels. Now, if you wonder why we just don't go and create just a stock model in our toolpaths, by having this kind of body of a stock, it allows us to open up our stock and select it for different things like our facing, our OptiRough, and so on. So it's really nice to have this, even though it creates a little bit of confusion of people having two stocks inside of MasterCam and they can never figure out how to turn it off. If you do, that does happen to you, make sure to refer to my MasterCam tips and tutorials at the bottom of the course page, okay? Make sure to know that before a test. So I'm gonna do a face and hit okay. Now, I'm gonna go to tools, and the stock is about 1 inch wide, right? In this direction, because we have, I believe, 2 inches sticking up in our Z and 1 across. A 1.5 inch face mill would be perfect. We can use a 1.5 inch face mill, and we should be able just to machine it in one pass, leaving 25 thou of overhang of our face mill, which is a decent amount. So I'm going to go to right click and say select library tool. I'm going to go to my filter, and I'm going to filter for my face mills. Now you're going to see that I do not have an 1.5 inch face mill, but we have an 1.5 inch face mill in our shop. We also have a 3-inch face mill. We could use that, but I like the 1.5 inch face mill for a nice finish on aluminum. So what can we do? Well, let's just exit this menu for now. And in this white box, if you hover over this white box, you can right click and let's create a tool. If MasterCam's general or our college's general toolbox does not have the tool you need, we can make the tool ourselves. So we're going to click on face mill and click next. And under here, we can set our cutting diameter. Mine is already set to 1.5 inches. I guess that's just lucky. The cutting diameter is really the diameter of the face mill. Our face mill has a cutting diameter of 1.5 inches. Now the secondary diameter doesn't really matter. It doesn't affect your tool path that much. It's more just about building the tool up a little bit, designing it. But in reality, we really have a secondary diameter on our tool. So we can, we can just set this as either, I don't believe it lets me do 1.5. See, intersect. So if you just do 1.51, that should just be enough to make it work in its mind. The overall length doesn't really matter. The cutting length, uh, 0.25, we just keep it about there. That would be how big your insert is on your face mill, but you guys don't really worry about that for now. Again, the more you set up your tool, really the better, because you could check to see if your tool's crashing, or if by setting your proper flute length or cutting length, you could see whether or not your depth cuts are going bigger than your flute amount, and it'll show up red in your simulation. But for us, it really does not matter. The shoulder length and the upper diameter really does not matter. But really for us, I believe the upper diameter is like basically 1.5 inches. It's just one big body of 1.5 inches. So if you really want to make it look like what it looks like, I guess this would be the most accurate. And we could just finish that there. We will make this tool 1, and we will go up from there. So the next tool will be tool 2 and 3 and 4, etc. So we'll move forward, my spindle speed and feed rate. I have learned with this face mill, and again, this just comes with experience. We will go through speeds and feeds later on in this curriculum. We will not spend too much time learning right now, just because I want you guys to focus on the basics of MasterCAM before we get into more of these parameters. But one speed I really like with this face mill is 8,000 RPM and 32 inches per minute. Works really, really well. It's about a chip load of 1 thou. I mean, obviously that depends on how many teeth there are. Right now we have it set as 4, which I think we technically only have 3, but that's okay. It's a good chip load. The plunge rate, because we're not cutting stock as we're plunging, we could just set this to 100. That'll turn to be our general rule now. I know I probably told you something in your previous course, but now we really want, if we're not cutting, we want to be saving as much time as possible. So by bumping it up to 100 inches per minute, we're saving lots of time. And rapid retract should always be checked off. You don't have to worry about holder now. We might get into this later in the semester about some holders. And again, really just by setting up your holder, you can simulate whether or not your holder is going to crash into your part or your fixture or your machine, whatever. One thing that sometimes might matter for you guys is your tool projection. So actually, if you guys remember from lab last week, we know that actually our tool projection is 2.85. Now it's not letting me just because my tool settings don't allow for that. But if I really want to, I could enter that projection of my tool here to get an accurate representation of how far it is. But we're just facing off 20 thou. Our face mill is not going to crash. There is 0 chance it's going to happen. So we do not have to take the time in setting that up. We will keep our cutting method as one way, but we'll change it to one pass because I believe we can cut this all at once. We want to make sure that we select our stock to leave on floors as 0. If you had, again, 50 thou, instead of cutting at Z0, which is where we're going to want to cut. I'm doing all this, by the way. Oh, I made the same mistake. I did not set up our plane yet. So after this, I'm going to go back and set up our plane. Seems to me like I like to jump the gun after I make the stock and forget about setting up my planes, but that is okay. We'll go back. But we're going to cut at Z0. We don't want to cut 50 thou above Z0. So if we said leave 50 thou on the floors, that would be leaving. It would cut to 0, but it would actually go 50 thou above 0 because you're telling it to leave 50 thou to where you're cutting at. Everything else should be fine. We're only facing off 20 thou. We do not need to worry about depth cuts. I always like to turn on clearance, and we can go down this menu here and select everything to absolute. I do like setting 1 inch as my clearance so that at the beginning and end of the tool path, my tool will always go up to the clearance before it starts moving around. Because we face my part at 0, we know as long as we're moving in our clearance, our retract, our feed plane, as long as these are positive numbers, we know that the tool will always lift out of the cut above the part before it moves to another cut or to do a tool change. So that's why we typically set the top of our part as 0, because we want to know that everything positive or above 0 is safe. So all these numbers are safe. Typically, I like to use 1 inch, 0.1, and 0.1 for my feed plane. So in between cuts, if it has multiple cuts, it'll go up to 0.1. When it goes to cut, it's going to wrap it down to our 0.1 before it starts to feed. And it's going to cut at 0, absolute. Actually, the top of stock here, we actually have 20 thou on top of our stock, so we should set 20 thou. It doesn't really matter if you left it at 0, to be honest, but it is nice for you guys to acknowledge that that top of stock is there. Because again, if I if I select, I'll put this back to 0. If I just select, the top surface here, you'll see that, oh, it sets it as 0 because I never set my plane yet. So we'll come back in a little bit and fix that. We won't worry about planes right now. We'll come back in and fix that. We'll make sure to turn on our flood. Now, again, I forgot to set my plane. My bad. Okay, you guys, might make a similar mistake, and that's okay. So let's set up a plane. So I'm going to click this little shortcut here instead of, or I could go to my planes tab and create a plane. But I like this feature just by clicking this. I am going to set up my plane. And for this lesson and our ENG-003, for this first batch, we can call it, we're going to be doing the back left of our stock. Our X and our Y will be zeroed out to the side and the back side of our stock. And our Z, we will make it so that it is the top of our part. Again, like I said, we want to make sure that our top of our part is always Z0. That way, after we face to 0, we know that anything above 0 is safe. Anything below 0, and there's a chance that we could be crashing. I am going to call this plane G54, okay, and hit OK. Now I'm going to go back into my toolpaths, and I'm going to go into my parameters, and I'm going to go to my planes section, and I'm going to set my planes to G54 by clicking this little menu right here, and then I could copy it over to my tool plane and my construction plane and hit OK. And there is my face. You can watch it. Now, if we really want to be nitpicky, this first little bit is a lot of wasted time. This first feed, it's cutting nothing but air, right? So if we're making one part, that doesn't matter. But when we start making, or even 100 parts, it doesn't really matter. But when we start making thousands or 10,000s of parts, you're wasting about 5-10 seconds per part by doing that. So you would want to try to minimize this. So what we'll do is we can change the along or the approach distance. That's one thing that we'll want, our approach distance, 0.75. Why don't we just make our approach distance like something like 0.25 and try that out? Did that shorten it at all? Exit distance, same thing. Let's do 0.25 and hit OK. That shortened it a little bit. And I bet if we do an along overlap and just make this like 1.05%, so that's as it passes by, how much further does the end mill go? There we go. So now our tool comes much closer to our cut before it starts cutting. A long overlap again is just so the tool starts off the workpiece and passes by completely, and then by the approach and exit amount, that's just adding to that a long overlap on each side to give you a little bit of a lead in and lead out. So there's our first face. Before I move on, I'm going to go to my planes and I'm going to make sure that my G54 is selected. So any more toolpaths that come from now, I want to make sure that the WCS, the C, and the T are set to my G54. If that is not the case, then my plane will be set to this top plane, which is not what I want. So I'm going to select my G54 and hit this red equal sign, which will send everything, my WCS, my cutting plane, and my tool plane to G54. So every new toolpath now will utilize that. So now that we've done our face, this is when, and this is where I'm going to be a bit different, this is where we're going to use the stock model feature, okay? And I'm going to show you something new. And in my opinion, this is much better than the way that Titans of CNC did it. So whenever you come in here, the first thing you should do is turn off your stock plane. If you don't forget to turn off your stock plane, you'll notice that your stock is created at a weird angle, not where your stock is supposed to be. So if you ever see that, you notice it's at a weird angle, kind of rotated 90 degrees, that should be a hint that you need to make sure that your stock plane is unchecked. Our initial stock shape, we already made a model. So we're going to go into model and we're just going to select it. And this is where we can triple click this part, or our stock. Make sure that you do not select your part on the inside. Sometimes it's a good habit to just turn off your part to make sure you don't accidentally select it. Because if you select your part as your stock, when you do your OptiRough, it's going to see your part, and your stock, which you made the exact same as your part. And it's going to be like, hey, I have nothing to do. There's nothing else for me to do because everything is machined perfectly already, right? So you would run into issues and it would give you alarms. Now, this is where we're going to differ. What we're going to do is we're going to go source operations. And because we've already faced our part, what we're going to do is we're going to set facing as one of our as our source operations. So it's going to take that stock model, but it's going to apply this toolpath to it and then create a model of whatever is left after it. And that will give our OptiRough an accurate representation of the stock that there is going into that toolpath. So if I give you guys a front view and I click off this stock level, you'll notice that it actually is slightly smaller. You can see it's actually losing a little bit of size to it. At the top, I could see the top of my part. When I turn this on, I don't see it. So there you go. Now with that, as you guys saw me, I did a front view here to show you guys that. Now what I want you to be careful of is anytime you use any of these features, right, front, top, what that does is it messes with your planes. Looking back at my planes, remember I set everything to G54? Well, every time you flip to a different side with one of these features, it actually changes your cutting plane and your tool plane to that side. So let's say right side, everything moved to that side. So you got to be very, very careful about the way you maneuver around your part. So I'm going to make sure I hit G54 and enter. Now, what I'm going to do is I'm going to show you a better way that you can maneuver around your part, okay? If you want to try to get those views. So first things first, I'm going to deselect this guy. Make sure to get rid of the stock. Make sure your only display selected toolpath is there and just click off of it. In fact, I can get rid of everything if I really wanted to, okay? What I want you guys to try out part, you don't have to, but this is fun. Again, each lesson and each tutorial, I'll probably throw something new in there and teach you a little bit something new that you haven't seen before. So under your view tab, I want you guys to try to turn on our on-off view sheets. You'll see at the bottom here, we have different view sheet 1 that was made, okay? Now, if we want, let's say, to be at the top of our part, so let's go top, just like this. Angle it, position it how you want it, and let's create a new view sheet. And let's call this, or we could just call this op1 because this is actually going to be op1. Okay. So whenever you go into one view sheet, let me call this one ISO. You can move stuff around. And as you, let's say I want to go back to my top. So whenever I leave this, this is how it's going to be seen when I open it back up. So I can go to op1 and give a top view of my part, or I could go to my ISO view and have an isometric view of my part. I could also make one for my front if I want one like this. Now, actually, before I did that, I should have hit front. Okay. And let's go back to my ISO and change this back to an isometric view. Okay. So now we can switch between all these different views of my part without changing my planes. So let's set this all to G54. I believe that won't change the planes. Oh, it does. So in this view sheet, let's actually just make sure that everything is selected to the proper planes. Perfect. So now when I switch between them, everything stays the same. The G, don't worry about that. Okay. Perfect. I like that. So this one, you could be the one that you move around in, and then you could always see this. So this will be, rename it, and we'll call this op2. And let's do another one and call it op3. And in this one, I'm going to go to the bottom of my part. Just like so. Set my planes equal to, and now I have all three of my ops and my isometric view. And then one last thing, now that we have all our views, let's go into each one and save it as a bookmark. And that should allow me to, let's say, maneuver around. And then when I come back, it resets to that view. So this is a much better way of moving through our part. In fact, actually, we might set different ones later, but for now, let's start with this and move forward with this. So little cool tip, something fun I like to use when I'm programming a lot. Okay, so let's get going. Let's get back on this part. Okay, so let's take a look at our stock model. Looks good. Okay. Fun. Okay. So we are going to do an OptiRough on the outside of our part. There's not much to machine. Okay. Now we don't really want to do an OptiRough on the inside of our part here. Really because we'll save that for roughing when we're in that third operation. Our tool can't really cut into this. Well, for one, it's going to leave radiuses and it would leave steps on this radius. It just doesn't cut there because it's flat on the bottom of the end mill. So we'll try to leave that. And again, I'll try out some different ways. We'll see. I got a couple of methods in mind right off the bat. We'll see if we can get it to avoid those areas. If not, we'll work to close off those areas for our machining purposes, okay? And we'll save that for op3. Really just want to machine the outside of our part. So let's get going. Let's do our holes on the top of the part. So we have 1032 tapped holes that go to a depth of 0.375 from my memory. If you want to open up the drawing, you can go back to your drawing and take a look. And by the way, one other thing I forgot to mention in ENG-003 is it's sometimes nice to look at the model and see what is going on, just to make sure that what components are fitting. These two guys are dowel pin holes, which we'll get into in a little bit. I don't believe that dowel pins are actually modeled in here, but there will be dowel pins that go into this hole. And these are going to be press fits. We could see I could tell that these are 0.2495 diameter holes. To me, that screams press fit. It's half a thou smaller than a 1/4 inch. A pin is going to be pressed into that. And then the other part we make is going to be more of like a sliding fit so that they're pressed in this side and it'll stay in this side, but you can take the other side on and off. If we go and do more of let's just do like if I just make this my current view, we can see what's going on the inside. So there's a bolt that goes about half the way down, a bit past half the way down this thread. So we want to make sure we get enough threads, especially for this bolt to go all the way down, right? The customer asked for 0.375 worth of threads. We need to make sure to give them that. But you would pay special attention if you notice that this bolt was really close to the bottom. But it already looks like the customer accommodated for some extra room at the bottom of the thread. The customer being me, and I know better to, make my holes a little bit deeper. Same thing for this bolt here as well, okay? So again, sometimes it's just nice to see your part, to see what's locating with it, to make sure that, like let's say for the dowel pins, we can actually take a dowel pin to the shop and make sure that everything is fitting the way we want it to. Okay, so let's go back to our MasterCAM file, and let's do our drilling tool pass. We'll get pretty good at these, as we know, whenever you do a tapped hole. By the way, guys, notice how this isn't tapped in MasterCAM. If I measure this, it is giving me a size of 0.16, right? What does that mean? So if you didn't look at the drawing, you wouldn't have known that that was a tapped hole. You would have assumed that it was a 0.16 diameter hole. So just really make sure to look at any drawings because that's going to give you the best information on what your holes actually have to be. So I'm going to go tool pass and I'm going to go drill, okay? And I'm going to select, let's actually go to my op1, get a better view. I'm going to select, actually I kind of like an isometric view here, 1 and 2, and hit OK. Go back to my ISO view. Tool. For this, we can use, just trying to think of what I'd want to use. We can use a 3/8 spot drill. why do I choose a 3/8 spot drill instead of a 1/4 inch spot drill? Well, I'm looking ahead and I see that we will need to chamfer these holes. I could use a 1/4 inch spot drill and just do like a contour around this hole right here to chamfer it. But the best way of chamfering a hole is just to do a drilling toolpath. And during your spot drill, just drill to the chamfer depth, or drill to a depth that creates that chamfer. To create that chamfer though, your tool has to be bigger than the hole. So this is a 0.25 hole. So for me to create that chamfer, I'd have to have a tool that's bigger than that. I know that a 0.375 would be more than enough. And you could verify that by clicking on your model. Let's just turn this all back on and analyzing what the diameter of this chamfer is, 0.27. So 0.375 will be more than enough. So that is what we're going to use. And that is why I could use a 1/4 inch spot drill, but if I'm going to use a 3/8 later on, why not try to minimize the amount of tools I'm going to use? And in this case, just use 3/8 spot drills for my entire part from beginning to end. So I'm going to select my library tool. I'm going to click on my filter. I'm going to select none, and I'm going to select spot drill. Now, in one of my previous tutorials, I set a tool diameter equal constraint. So I'm going to turn this off. If you ever have that on, you could utilize that feature to help find drills. In fact, in this tutorial, I'll probably show you how to do that. But we want to make sure to turn that off, or else no spot drills would show up to us because it was setting a constraint that it had to be equal to 0.136. I'm going to choose my 3/8 spot drill for this job. I'm going to double click on my spot drill and I'm going to click next and do 2 and hit finish. Okay. For my spot drill, I'm doing spotting. I like really drilling, not chamfering. Again, a good speed is about 8,000 RPM, and I like to slow it down to about 25 inches per minute, which is a good feed. Again, we'll get into speeds and feeds later on. When it's drilling, slowing it down is a bit nice. Again, this just comes from personal experience, and I'll get you more of that mindset later on. For this, we're just going to do a simple drill and counter bore. We're going to go to our linking parameters. We're going to turn on our clearance and set that to 1 inch. We're going to make sure everything is incremental. Start clearance only at start and end of operation is one that's nice to turn on. Our retract is 0.1, I like. Our top of stock is the top of the part still because we face it down to 0. So top of stock is 0. And the depth, typically I might go to something like minus 0.05. But my question to myself is, do I want to also chamfer this part for the customer at the same time? In this case, I believe, yeah, maybe let's just make our hole or our spot drill a little bit bigger so it comes already kind of deburred. We don't have to burr it or deburred ourselves. To figure that out, though, we need to know what size our tap is. So we have a 10-32 tool. We can look up 10-32 thread size. A 10-32 thread is 3/16 of an inch in diameter. So the external thread is 3/16. So what I'm going to do is I'm going to use this calculator tool. By using this calculator tool, we can actually create a chamfer a certain diameter, which will set it to a certain depth. So 3/16, right? So 0.1875. Okay. But we want to add a little bit of a chamfer. So let's add maybe let's do 10 thou on each side. So let's do a 0.02, add it to the diameter. So that creates a finished diameter 0.0275. And I want to check off overwrite depth. What this is going to do when I hit OK, it knows that the chamfer size I want is 0.2075, which is the external diameter of the chamfer, or the biggest diameter. And it's going to calculate what the depth the spot drill should go to get that chamfer size. I'm going to hit OK, make sure to check off overwrite depth, and that is the depth I should be going to. Now, because this chamfer isn't modeled in MasterCAM, it will look like we're cutting into our part, and it might give us like red saying, oh, you're cutting into your part, but we know that is something that actually we want. Now you might want to consult with your customer, because sometimes if they don't ask for a chamfer, they might not want one. Maybe the engineering specifies that they can't have a chamfer, but typically when you have a thread, it's nice to have a little bit of a chamfer to help start the bolt going into the thread. So um, let's say I talked to my customer and I said, hey, you know what, we should add a chamfer here. It'll make it better for you. And I talk to the customer, being me, and I say, yes, that is okay. Let's do that. Because we are spot drilling and we're not going through the bottom of the part, we are not going to turn on tip comp. We can skip down again. If I don't go through a menu, you don't have to worry about it, okay? Make sure our planes are right and our coolant is going to be turned to on and flood, because our machine has flood coolant. Okay, now we can see if we backplot this feature, notice how it goes to our feed plane. It cuts quite a bit in. Oh, whoa, that's a lot. Okay, that's not what I wanted. Interesting. So let's take a look at what is going on here. Let's go back into my linking parameters and let's take a look at this. Ah, I didn't set anything to absolute. Let's try that. There we go. Setting everything to absolute. We can see our spot drill actually makes our hole a little bit bigger. Now it looks like it's doing quite a lot, but remember when we open up the tapped hole, it's actually going to be bigger than the model is showing. So in the end, we should have a nice looking chamfer there. Now we are doing the 1032 tap. Now, when a customer asks for a tap, they're not going to specify that they want a roll tap or a cut tap. Some aerospace industries will ask for roll tap specifically because it will not create stress cracks. But myself, as the person making this part, I get to decide, do I want to use a cut tap or a roll tap? Typically, if the size of the hole is less than half an inch, I will use, or even less than, let's say 0.375 and down. So 0.375 and down, I'll use roll tap, and then about half inch and above, I'll do cut taps just because of the forces involved. So let's use a roll tap. Now, before we use a roll tap, obviously we got to drill out the pre-drilled hole for that tap size. So we're going to consult our tap drill chart. Now, because we're using a roll tap, we need to make sure that we find a tap drill chart that is specifically meant for roll taps. The tap drills are different for a cut tap versus a roll tap. Okay, so a cut or a tap drill that is meant for a 10-32 cut tap is not going to be the same tap drill that is meant for a 10-32 roll tap. If you get these values mixed up, you will crash your machine. So that being said, we can look at our chart and find 10-32. Just bringing something else up in the background right now. Okay, so looking at 10-32, and maybe myself, I'm just going to double check on my drawing that it is a 10-32 tapped hole, which it is. I just want to make sure I wasn't confusing it with a 10-24. So looking at my roll tap drill size chart, I can see that I need a 4.4 millimeter thread, which leaves us with 78% of threads, which you can look into what that actually means. But 4.4 millimeters. Now, one problem here, guys, is that I don't have millimeter drills. Okay. By the way, I'll upload this roll tap chart online. If you ever download or if you ever look up tap drill chart, typically what will show up is cut tap charts. So if you just see a tap drill chart and it doesn't say if it's roll or cut, you're going to assume that is cut. You specifically have to look up roll tap. This one from Haas is one of my favorite ones, but a lot of the drills they specify you to use are millimeter. So a 4.4 millimeter, we can look at what the equivalent of that is. So remember 4.4 millimeters. I looked up online drill decimal equivalent chart and found this site. So I'm going to go down and find a 4.4 millimeter metric drill size, which, oh, lucky me, it does not tell me what that is. Oh, actually on this right side, equivalent. Okay, 4.4. Okay, what about 4.394? We have an option between 4.394 and 4.496. Now, to give you guys a little bit of a feeling of what that is, so if we were doing 4.496, we're 0.096 over what we were looking for, which is about 3.5 thou over. Now, choosing a tap drill that's about 3.5 larger isn't the worst thing in the world. It takes out 3 thou more of threads. So I kind of like that. I like taking more than going the opposite way and taking less, or like leaving more thread, because then we're risking breaking our tap. So we'll go with this, a 4.496, which is a 0.177, which is a number 16 drill. So we'll use a number 16 drill for this part. You guys are probably remember doing the Titan 1M, and for a 10-32 roll tap, we used a number 16, right? Either or a number 16 or a 17 would have worked in that scenario. Now what I'm going to do is I'm just going to copy this and paste this toolpath just because I'm lazy and I don't want to reselect my holes and some of the features. And so when I right click, I just said copy. Now for some reason you can't click in here and say paste, but if you just hold Control and press V, it will copy that toolpath for you. We can go into the parameters. We're going to start right back at the top, and we're going to select our tool first. So select library tool. I'm going to filter for a drill. And instead of me having to search through all the drills that are available, I'm going to set an equal to filter as well. And I know that the drill we're looking for is 0.177. By the way, make sure to never turn off any of this. If you hit none by accident, no tools will show up. So keep all these selected. And I'm going to hit OK. There's my number 16 drill. Perfect. Let's double click on that tool. Let's go and set this as tool number 3 and finish. When I'm drilling, I normally like to slow down my speed a little bit. For smaller drills, I should be going a little bit faster with my spindle speed. For bigger drills, I should slow it down a little bit. So for this one, I actually like 8,000 RPM as my spindle speed. Again, you could just do the calculations if you wanted to do cutting speed times 4 divided by diameter to really get what it could be. But for that, you actually need to know what the cutting speed of the tool is for the specific material. But again, we'll talk about that in the future. Now, I talk about this in ENG-003 as well, but a little trick I have for you guys. Whenever you are doing dynamic or like OptiRough with the tool or drilling, this works for both of those. My cheat code is set your spindle speed, and then under feed per tooth or chip load, what you can do is set it as your drill diameter, but make your drill diameter move the decimal places 2 decimal places to the right. So instead of 0.177, let's do 0.0017, and it doesn't have to put another 7. That's just redundant at that point. And then click on feed rate, and that'll automatically set the feed rate. This is a good hack for aluminum whenever you are doing, again, like the OptiRough or drilling. If you want a good starting point, even roughing aluminum, it could work as well without doing the finishing, we want to slow it down because we want to get a better finish. Drilled holes, though, drills want to get pushed, so we're not really worried about going slower with a drill. They want to get pushed hard to get the proper cutting out of the drill. So this looks good to me, 8,027.2. I was kind of thinking 25 off the bat, so that's about right. Let me just double check. Okay, everything else is good. Cut parameters, because we are drilling 0.37 deep, which is about like 2 times the diameter of the drill. We'll just do a little chip break. We're not going that deep. We are going to go a little bit deeper than 0.375, but so we'll turn this on. And my rule from last semester, just set your pecs to the same size as your drill diameter. Remember that chip break, it's going to peck down and it's going to lift up slightly and then drill down and lift up slightly, drill down. So it's not going to come all the way out. Whereas a peck drill, would actually come all the way out in between each one. So if you're really having troubles with coolant getting to the bottom of the hole, that's when you would want to use a peck drill. Chip break is much better just for staying in the cut. The only thing you're doing by breaking the chip, it's in the name. It just breaks off the chip so that you don't get these long stringy chips. It's really nice if you're drilling past, 2 times D or diameter of your part. Okay. Clearance is 1 inch, retract is 0.1. Top of stock is 0. And my depth, I could, select the bottom of my hole, but this is not going to be accurate for me. That did not work out. I know that my drill depth, or my tap, I'm supposed to get 0.375 worth of threads. That means I need 0.375 worth of threads, okay? So, whoops. When I drill my hole, whoa, I didn't mean to get a straight line here. Straight line's nice though. Not gonna argue with that. Why did I do that? Interesting. Okay, so that's my hole in my part. Whoa. There's my threads. So I need to make sure I have 0.375 worth of threads. Okay. That means my tap not only should go down to 0.375, but my tap should probably go a little bit past 0.375 because taps, depending on the taps you use, I'll just draw it straight, pretend that it's threaded. Either sometimes have a little bit of a taper towards the bottom of the drill. This is really weird. I haven't seen this before. So sometimes there's a little taper. So they lose the threads. So even if your tap goes down to 0.375, you're only getting threads probably up to this point right here. So you're not getting 0.375 worth of threads. So we should look at what our taps look like. But let's at least make our tap go probably about 50 thou past. And 50 thou will be a good amount because we are using a bottoming tap. So 50 thou will just make sure that we get full 3.375 full threads. So that gets us to 4.425. Now we're going to want to make sure, because our tap is now coming down, by the way, the shoulder of the tap is coming down to that depth. We need to make sure that we have extra room at the bottom for chips, or so that our tap does not bottom out on the bottom of the hole. But also sometimes when chips are made, they can kind of clog up down here and eventually snap if we don't have enough room. Now there are some taps that have spiral flutes on them. They're called spiral flute taps so that the chips, actually we're using a roll tap, so this doesn't matter. But if you were using a cut tap, spiral flutes are nice because they'll let the chips come out of the hole. So let's drill down to 0.5. We could see if that will work. And we could always come and modify it afterwards if we think it's not enough or too much. So I'm going to go to minus 0.5. I've kind of already accommodated for the tip comp, so I'm not going to worry about that right now. We'll see. We'll see what the tool looks like later. Okay, so we'll keep tip comp off for now. And you'll do this anytime you have blind holes, by the way. Through holes don't matter as much, but blind holes are where this really comes into account. Hit OK. That looks pretty good. You can see I'm not really interfering into any other holes or part of my part, so that's nice. Now I'm going to copy this and paste this. Again, Control V. And I'm going to go back in and just change this to a tap now. So select tool, filter, get rid of this equal filter, turn on my right hand tap. We always right hand. The way I remember it is, most people are right-handed, so most people will always use a right-handed tap. And we'll find our 1032. Nice and easy to find. Taps, very easy. Unless you start to use bigger taps, you would slow this down. But this works up to about 3/8 of an inch, I would say. but 1000 RPM is a great spindle speed. If you click anywhere on your screen after you set your spindle speed, your feed rate should automatically be set, because remember that for a tap, your feed rate is your spindle speed divided by your inches or threads per inch, right? So that's automatically set. You can't mess that up unless when you build your tool, you don't tell it. Like in here, you really got to make sure if you do try to build your own tool, this is a very important thing to set in your parameters, okay? Is your threads per inch. Cut parameters, we're going to switch to tap. Okay, clearance is going to be 1 inch, 0.1, top of stock is 0, and depth, we can go less. So again, let's accommodate for 50 thou. I think I said 0.425 is what we want to go for. And again, I've kind of already calculated for the tip comp. The tip comp technically doesn't really work too well right now because we didn't really tell it the tip size, like the angle or how big the chamfer is at the end of the tap. Or the drill, it's standard for across drills, but taps are always different. So 0.425 should work. What I like to do is do a little view, and maybe I'll do a front view of this. So we can see our tap comes down, and we should get at least some full threads at this point right here. And our drill should go deeper, as we could see it is. So that means that our tap isn't going to bottom out. That's really good. That is op 1. Two more to go. For op 2, I'm debating whether or not just want to double check everything's good here, and we could simulate it. Stock setup. And there we go. We're going to go up to and say op 1. Keep this nice and clean. Let's go up here. Don't want to click on this because it will make the folder inside of op 1, which we don't want. And we're going to say group, and we're going to say new toolpath group, and we're going to call this op 2. Okay. Now, for my op 2, I have to create a new plane to utilize. Before we do that, let's create a stock model to see what our part looks like after op 1. For this, instead of selecting my initial stock shape as my model, I'll use my previous stock model I made, which is stock model number 1. I'll go source operations, and I can even just select entire of op 1. Actually, we already did the face, so let's just do the 3 other ones other than the face and hit OK. Oh my gosh, I forgot to do the OptiRough. You guys are probably laughing at me, right? It's funny, I went straight into we missed some stuff. That's not done for op 1. Remember I told you guys I'd be going back and forth and forgetting things? You know, it is 10 p.m. and I had to deal with you guys for 6 hours today. So that is my excuse for why I forgot the most important toolpath. How could I? Let's keep 10 thou for my wall and floor stock. So we're going to do an OptiRough here, guys. Triple click. Now, actually, let's deselect this. I'm going to try this out. I'm still playing around with this toolpath in MasterCAM. Let's turn on this avoidance, and let's click add these as avoidance features. Let's tell it to leave 10 thou on the walls and floors, just so if it does go in there, it doesn't really cut. We'll see. Tool path control, boundary chain. You guys know, well, actually don't know. I did mention this in class that typically I like the bottom of my outline of my stock to be my boundary chain instead of my part. It just works better. That way it just gives your tool more freedom to move. And sometimes when you have wonky parts, if you set it as the outside of your part, it just doesn't work out. So strategy is going to be from outside, compensate to outside, and offset distance, something like 1/2 inch, which is probably going to be the diameter of my cutter that we're going to use. We will see. Maybe 3/8 end mill. Doesn't matter, but that's okay. Yes, okay. That did a lot of extra stuff it did not need to do. And why did it do that? I know right off the bat. I didn't tell it any parameters. I just pressed go. Oh my gosh, guys, I am tired. Okay. Let's go to tool. Let's select a tool. And let's press, let's take a look at our model to see what size we can get away with for our part today. Actually, I mean, there's no limiting factors. The only internal radius is this tool right here. So you know what? I'm going to use today, I'm going to use a 3/8 end mill because I know that the other class is going to be using the 1/2 inch end mill and the 1/4 inch end mill. So let's stick to a 3/8 end mill for today. Now, do I care that now this tool is technically 5, but it's the second tool in the program? No, does it matter? It does not. Is it nice when it's in order? Yes, but that's okay. When I do my OptiRough, we're gonna want to crush this material nice and fast. So let's do 12,000 RPM, crank it right up, and let's do my little trick. Remember I said set it to your tool diameter, but 2 decimal places over. That gives us a feed rate of 180. That's pretty good. We could probably even crank that up a little bit more to 200 for fun. Our plunge rate, let's set that to 100. Stock, we do want to turn on rest material. And we're going to select one other operation, and we're going to select this stock model, number 2, right here. Our step over is going to be, let's do 15%. Anywhere between 10 to 15 is a pretty safe number for OptiRough. Our step down, we can utilize the entire flute length of our tool. I know that we have a tool that has 0.75 worth of flutes, but we'll use a 0.75 inch step down. And we'll turn on step ups, keep it at 10% for now. Our minimum depth is going to be the top of the part. Our maximum depth we can set to be the bottom of our part. And then we'll set it a little bit deeper. So 1.4, let's let it go to 1.45, 50 thou past that. Our clearance, we can just change it to 1 inch. And our back feed rate, we'll set this to 500. This is when it's, if you see what an OptiRough looks like, it cuts and then moves backwards. This is the speed it will move in between those cuts, which is exactly what we want. Everything else, don't really worry about. We don't need to worry about entry motions. We're not cutting any pockets. Everything looks good there. Let's turn on our flood coolant and let's take a look at what the toolpath looks like now. I'm going to assume it's something I don't like. Okay, it's still going in there, but it's not touching. It's not going to cut that. It will cut material out of that, which I'd rather just rough it in a different point. So let me try something I really don't do too often. Let's add another level and let's call this, we'll just call it maybe patch. And let's go to our surfaces tab. And what we're going to do is we could extrude, loft, flat boundary, defined by a closed chain. Okay, what if we just do, so let's use our wireframe and let's curve some edges here. Let's do curve. So by the way, this is this curve one edge feature. And what this does is it creates wireframe on our stock edges. So it takes our solid and it actually creates now selectable. See how I can't select this edge, but now I can select the wireframe there. Let's go back to our surfaces and let's do a flat boundary. Now, actually, let's do one more thing. Back to wireframe. Let's draw one line endpoint, and let's draw it from this point to this point to make two enclosed shapes, one on each side. Then let's go to surfaces and let's do flat boundary, and let's select this loop as one boundary. And let's hit the blue check mark, and I'm going to hold shift and select this line as well and click down this and select OK and hit OK. So that should allow us to avoid that area if I am correct. Let's go back to our toolpath model geometry and let's redo this. So let's click on this entities and let's clear the selection. And actually, yeah, if we just, you know what, if we just, probably didn't have to do that. Let's do that, hit end selection, and let's do some avoidance regions. Let's clear that, and let's set these as avoidance regions. And then we'll just tell it to leave 10th thou on it. So just like it would the walls here, it'll leave 10th thou on if we do this now. Oh yeah, that's exactly what we want. It's not really machining that much, guys. It's almost like it's just doing contours at this point, but you can see how we properly avoided that area by creating a little filler between that. So it's going to rough it out. It's already faced on the top. It's exactly what we want. It should come down to the bottom of the part and cut. Nice, beautiful, guys, like that. Okay. So now we're done with that. By the way, when I imported this toolpath up here, I moved this red arrow up here. So wherever this little red arrow is where your toolpaths get entered when you create them. So if I create another one, it's going to go below. So I will create one more toolpath, which is going to be my contour. Okay. I will select, I got to change the solid selection, and I will change, I will just select, let's say the bottom of this face as my contour. I will have to switch the directions to this direction to make sure I am climb milling. I will hit OK. My tool is still going to be my 3/8 flat end mill, but now I'm finishing. So I'll keep it at 12,000 RPM, but let's slow down to something like 1 thou chip load. If you are curious what chip load is, please, even if you're working on this assignment first, go to my ENG-003 video. I do have a point in there where I talk about what chip load is, okay? It really is just how much material each flute takes off each time it spins around, or the thickness of the chips that come off. The thicker the chip load, the higher the pressure. So whenever we're finishing, we want to have a lower chip load. That allows us to get a really nice finish. Less pressure on the tool creates less vibration. Plunge rate is 100. Our retract rate will set to rapid retract. Cut parameters. I'm going to change this from compensation type from computer to where. This will allow us to measure our part as it's getting machined. If we notice it's being machined too much or too little, we can control what a where value on the machine control. So we could say, you know what, this tool is cutting 1 thou too big, or this tool is cutting 1 thou too small. So when it cuts the profile, it can automatically adjust knowing that it's cutting big or small. And that's how we really dial in parts on the machine. So in our first class, if we have time, or future classes, we'll look at how to measure our parts and make sure that we are getting proper tolerance is being hit in our part. Because we are finishing, we want to make sure walls and floors are set to 0. We are going to want to turn on depth cuts, and we'll set these to 0.75 inches because again, we know that we have a tool that has 0.75 inches worth of flutes. We do not need a finish cut in our depth cut. That is not something you typically will need unless you have a floor at the bottom, which we don't. We will just keep tool down. I always like to check that off. Lead in, lead out. I might just want to shorten these a little bit. So let's just do 0.05 and 0.05. Really just a little bit of a lead in, lead out's nice, just so that it doesn't lower as it's touching the material. So just by doing 50 thou, and we can copy this across to our lead out as well. That just makes our entries and exits just that much smaller. See, nice little tiny entries and exits. And there we have a nice contour. Now, one last thing I didn't check is whether or not my coolant was on. And I didn't even set a depth. Oh my gosh, it just knew. See, like I tell you guys, I'm crazy. I just forget things all the time. I get ahead of myself. I will say though, trying to talk to you guys and explain everything, I think distracts me. So I'm gonna blame everything on having the conversation with you guys as I'm programming. Top of stock is not 1.4, top of stock is 0. Depth is definitely 1.4 though, but that is absolute, so we gotta make sure it's absolute. There are times and places for incremental. I will probably show you when we would use incremental depths when we get there. We do not want to, we do want to break through actually. Let's do a breakthrough of 50 thou. And turn our coolant flood on. Beautiful. There we go. So that's the end of op 1. We will now go to, did I call this op 2? This is actually op 3. Rename. This is op 3. This is op 2. So let's keep this nice and organized. Okay. So op 1 looked like this, right? 1 second. Let me get let my taskbar go out of the way. Leave, leave, leave. I don't want you anymore. Okay. So our op 2, either we could flip our part like this. So you see the radius is facing the back of the vise, or we could flip our part like this, where the flat is facing the back. Now for me, I don't have a preference. Let's go with whatever it is in our op 2 view. So this can be, actually, I kind of want to flip this around. Is there? Oh wait, I know I could rotate my part if I want to. Just my screen. Whatever. Okay. For today, for setting the plane, I'm just going to rotate this around just like this. I actually like my sharp edge being at the back just because it's going to make my plane setting a little bit easier. But actually, you know what? Let's make it hard. Let's make it the hard way so you guys can see how to do it. So for this part, I want my x0 for my op2 to be the left of the part and my y0 to be the back of the part. You will see when we take this to the machine, I strategically put them there for a reason. Because when we put our part in our machine for op2, we're going to have our vise, and we're going to have our vise. Now, we're going to talk about how it's going to be very hard for us to set our stock for op2. Because what's going to happen is with our probe, there's going to be a piece of stock around on the back side of our part, right? Imagine, so coming off this, there's a piece of stock here. So if I try to take my probe, let's look at it from this way, pretend that my stock for op2 looks like this, even though I think it's the other way. When my probe comes in, and I try to touch off the side of this part, guess what? My stem is going to crash right here, and I will not be able to actually measure that side of my part. Now, we cannot measure the side of our stock for op2, and we'll talk about why in the lab. But we still want our plane to be the side of our part. So, with that being said, what we could do before we put our part into our machine, so our stock is no longer there, and pretend the part's not there, but we just have our vise. Our vise is nice and open. So from the, I don't know, the vise looks like this, right? We have our parallels in here. That was bad. Draw it like that. I can stick my probe in here, and I can measure off this face of my jaw. So my probe will measure off that face of the jaw, and that will set this jaw face as Y0. I can do the same thing and touch my probe to the side of the jaw, and that will set this as X0. So now if I use a tool to align my part exactly up in the X along to line it up with the exact side of my part or my vise, now my part has effectively been located to the left of the part being at X0. And because the back fixed jaw, it never moves, when we bump our part up to it, it is going to also, the back of the part will be aligned to Y0. And then we'll also measure off the top of our parallels because our stock is going to be in here like this later. We can't measure this as our stock. So what we'll do is we'll measure our bottom of our top of our parallel, and then we're going to move our Z0 up the thickness of the part to get to where the top of our part is. Okay, and if that's confusing to you, that is okay. We will learn that in class next week. But we'll make sure on our setup sheet, you'll see me describe this to the operator, okay? So that's why I'm doing the back left edge specifically. I am going to now create a plane. Now notice that there's nothing here for me to grab. Okay, that's okay. Just put your plane down somewhere to start. Probably best starting point is just at the radius or the tangent of one of those radiuses. My Z is sticking up. Let's make sure we rotate our planes so that they're the way they should be. Minus 180, enter, enter for me. You just got to flip it to this orientation. And my Y is already at the back of my part, but my X is not. So all you got to do is grab the long shaft of the X and drag, and all you got to do is hover over an element on the left side and click it. And now your X has been set to the left side of your part, your Y is the back side of your part, and the Z is the top of the part, as it always should be. Now this plane is going to be called G55. And what we're going to do is we're actually going to check off manual. Now, -1 is going to be our G54. When we go up 1, 0 is G55. Now, why do they do that? I do not know. Why don't they just put G54, 55, 56? Maybe because of different coding systems, I guess. But in my opinion, that would be a lot easier. But 0, I believe, should export as G55, okay? And that is what we want on our machine. So I'm going to hit OK. So up to, we will make sure that we probe in G55. I'm going to now make sure my red target is below the stock model here. And what I'm going to do now is, because I have this OptiRough, notice how my stock model still doesn't show all that stuff being cut. Let's right click, or let's open up the parameters of the stock model, and let's go to source operations and make sure that those contour and the OptiRest are also selected. And let's regenerate this toolpath stock model. So this is what our part looks like coming off of op1. Look at that beautiful thing. Nice. Looking good. Okay. So we got to get, all we got to do for op2, there's no features on the side, but all we're doing is facing down the stock that's left over. Now we can go about this a couple different ways. We can use an end mill, our 3/8 end mill, and do like an OptiRough style cut and then a finish, or we just take our face mill. Now the amount of material that's there should be not too much. So if I take 1/8 of an inch depth cuts, that should work pretty well. So let's do a facing toolpath. And we might change this later. Who knows? I might not like it. Let's turn on my level and turn on my stock. And I'm just going to select this face of my stock as my stock boundary. I'm going to use my face mill. Remember 8032? Heck, let's keep all that the same. In fact, I could have copied and pasted my old face. Now, this one, we are going to do not one pass, not one way. We'll do zigzag because we want to cut one way. We're not going to be able to do this all in one cut. because there's a lot of stock there. We're gonna have to do depth cuts. So if we cut across, it's gonna drop down, cut across. That's my hope. Everything else, let's keep it the same. Stock to leave on floors, 0. Depth cuts, yes. Let's turn on depth cuts and let's do about 1/8 of an inch is what I like to max out my cuts at. Now, we don't want our last cut to be 1/8 of an inch because that would cause a lot of vibration and not the nicest finish. So let's also turn on 1 finish cut. So because we have a floor, let's do depth cuts, but we'll turn on 1 finish cut and we'll make that step 10 thou or 20 thou, whatever you want. Keep tool down, okay? Depth cut direction step down, definitely. Linking parameters, okay, this is important. So 1 inch, 0.1, 0.1, top of stock is right here. Now, something's wrong here. My planes aren't right. I gotta fix these. I gotta make these my G55. Let's do that again. Top of stock. So actually, guys, I want you to be very careful here. Retract and feed plane, very important that we change these because you got to know that we have more than 0.1 inches of stock onto our part. If you keep 0.1 of stock or 0.1 retract feed plane, our tool's going to rapid to 0.1 when in fact there's, let's see how much stock on our top of our Z0. We have 0.58. That would crash. So our retract and feed plane needs to be above our top of our stock. So let's make this something like 0.625 or something like that, 0.625. Now our depth we're going to cut to is Z0. Okay. And again, you should see that your feed plane, clearance, and retract are all above your top of your stock, or else you're in trouble. That's a new feature, these like colored planes in MasterCAM. I do like them for this case because you looked at and make sure that you're not crashing. Coolant is already on. Yes. Okay. No, I don't like that. We don't want it to zigzag. We want it to cut all at once. Now, what if I do one way? No, I don't like that one. Don't like that either. One pass. Okay, that's exactly what I want. Down, back, down, back, down, back, down, back, down, back. Done. A lot of extra material. So that's why, having extra material is nice, but it becomes a pain in the ass because you have a lot to machine for your op2, and there is a lot of waste. But that shouldn't be bad. It's not too big of a part, so it shouldn't take too long. Okay. And that's it. That's our op2. Done. Let's go and right click and create a new toolpath group. And by the way, for this part, guys, because of the time constraint, I'm not going to do any chamfers or like stuff that's not in the model. I'm not going to do any chamfering around the parts. You guys will just deburr it yourselves in your own time when you have when the part comes off the machine. So let's make another stock model to see what our stock looks like now. Again, this has no use to you necessarily, unless, in this case, we actually will be doing an OptiRough, so there is use to us. But because before an OptiRough used to always make a new stock model to show an updated model of what the stock looks like. But it's nice to see after each op what it looks like. It cleans things up a little bit. So we're going to do stock definition, stock model. We're going to refer to stock 2. Stock model 2, and the only operation that's happened since is facing. So just hit that as okay. And this is now what our part is looking like. Good. So now we're going to do op3. Let's make op3 face this way, just like this. I just like to see if I have a choice between the pocket facing me and away from me, I like it facing me just so I have a better sight of my tool. Instead of my tool going to the back of my part, it'll come to the front. We'll have a better view. It's the only reason why I would choose it. Again, doesn't really matter, just in my opinion, I like that. So we're going to start with an OptiRough here, guys. and we are just going to select, well, we could select the entire part. That's fine, because it tell that there's no stock anywhere else, so it really shouldn't try to machine anything else because it's all been machined already. Avoidance, we don't have to worry about. Just keep that. We'll keep 10,000 floor and walls. Toolpath control. Normally, again, you would set it as your stock, but because the stock is already cut, we could make it. Well, we don't really have a nice boundary, do we? Maybe we just make it the outside of our stock then, just to make it easy. Instead, the other option would just be draw in some wireframe to tell it what our boundary is, but let's just keep it simple like this. Everything else should be fine. Our tool, we'll go back to our 3/8 flat end mill, do our 12,000 and 200. That's what we did about, right? Is that what I did? Yeah. Don't worry about plunge rate. It's not going to be cutting or plunging as it cuts. Rest material, but we're going to base it off of this stock model instead. Step over 15%, step down 0.75%. That's all good. Steep, shallow, maximum depth. We can turn off our stock so we can see inside of our part. Our max depth is right there. Our linking parameters. All that's good. All that's good. Good, good, good. Planes. We're going to change this. Oh my gosh, we didn't make a plane. How could I even be making a toolpath without a plane? Wow. I'm all over the place. That's okay. See, my tool's coming from the wrong place. Funny, silly Greg. Again, we'll make this back left edge just to keep it simple. Ooh. Or do we? This part's 2 inches big. Yeah. What if we do that? Oh, but that would get in the way of our face. Right? Unless up 1 is there. Sorry guys, I'm just planning something out here. No, you'd have to do. Oh no, you can't do that. Okay. Op 1 and 2 can be together, maybe. I'm thinking of putting multiple parts on vices at once. So op 1 and 2, because of the same dimension. No, they're not the same dimension. The op 1 has stock. So we'd have to. Okay, yes, let's keep it here. That's fine. Let's do that. I'm planning ahead on how. So I imagine we have 2 vices on the VF4. The left vice is going to be for op 1. And then we need another spot for op 2 and another spot for op 3. But we could just keep our op 1 on the left vice, and then we'll do op 2s on the right vice. But we'll just do op 2 and 3 separately at separate times. But because the X and Y, because the X0, Y0 is in the exact same place on each of these setups, you'd just have to change your Z0, but that's it. Okay, hang with me here. Again, we'll talk about this in class. G56, and let's change this to manual, and let's do 1, which should be G56. Okay, let's go back into this parameters here, and let's change our planes to G56. I don't know why I always forget planes. I'm so ahead of myself sometimes. Beautiful. And then we just got to do a finish. And I think the best toolpath for finishing this, because it is kind of like a pocket, but it has some open areas, the best thing would be an area mill. Area mill is a really good toolpath that I like to use whenever possible. Let's go 2D and let's do area mill. Our machining regions is going to be this inside here. We could stay inside, but we can add an air region, which would just be this line right here, which tells it that it has to stay inside this box, which means it won't cut into these walls, but it will know that this side here is air region, which will allow the tool to go outside. Now it says chain is overlapping itself. Again, I could tell you right off the bat, I forgot to change my planes to G56. So you can see how these planes really become an issue for people, right? Got to be careful, okay? Tool, we'll keep that 310 mil in there. We'll do 12,000. We will do feed rate of, oh, oops, just pulled on my mic. Hopefully it's still going. Yep, that's good. We'll do a feed rate of, again, about 1,000, 48, sure, plunge rate 100. Cut parameters, step over because it's a finishing pass. We can do quite a lot, so let's keep it at somewhere at like 50. Probably even do a little bit more. Stock to leave on walls and floors is 0 and 0. Depth cuts, nope. We're just finishing. We're already finishing, so we don't need to turn on finishing passes. Clearance is 1 inch. Absolute. Only at start and end. Absolute. 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 Feed plane 0.1. Top of stock is 0. Retract. Let's also put this to 0.1. And our depth is going to be the bottom of this pocket. No breakthrough. Entry motion. There shouldn't be any helixes needed, so we won't worry about that. Let's go to planes. That's good. Coolant. Let's turn that on to flood. Let's see how this toolpath works. Beautiful. Love it. Beautiful toolpath. Okay. We've got some holes to make. So first thing we're gonna do is we're gonna spot drill both the sets of holes. We could obviously spot drill, then tap the first holes, then spot drill the second set of holes. But why would you put your tool, your 3/8 end or 3/8 spot drill in when you know you're gonna have to use it for the other holes anyways? There's nothing stopping you from using it right away. So we're going to use the spot drill for both of these holes. But because I am going to be trying to get this chamfer on this hole, and I'll probably put its own chamfer on these holes, we'll have to do separate chamfer mills. So let's actually copy and paste this old drill counterboard from over here, just so we don't have to reselect everything. Paste. Now the first thing you're going to want to do is go and change your planes, because the planes are different in this one. So the more you copy and paste toolpaths, the better. Then we're going to go into geometry and we're going to delete out these guys. Oh, there goes my mouse. And we're going to rechain them. So that's all you got to do is really change the plane and change the geometry, and then we'll change the depth as well, the linking parameters. So we're going to set, let's start with this hole and this hole, 0.201 diameter. If we look at a drawing, this is a 1/4-20 thread. So all we're going to do is go to our linking parameters. Everything's going to be the same. Top of stock is 0, but we're going to go to our calculator and let's do 0.25. And again, we're going to add a 10th chamfer to each side. So let's add 0.2, 0.02. Sorry, so 0.252 or 0.27. Overwrite depth. Okay, there we go. No tip comp. Everything else should be the same because we already set all the speeds and feeds for that tool, so we don't really have to worry about it. Beautiful. Now we're going to do the same thing. Copy, paste. This time I just copy this one because the plane's already set up. We just got to change, for one, we'll change the geometry, delete these ones out, select U and U, okay. And then we're just going to go to our parameters and we're going to set our linking parameters. We're going to change this, and it says finished diameter. Well, we can take a look at what that finished diameter is supposed to be for our chamfer. It's going to be 0.29. Really? Again, my mouse fell on me. Some technical issues. override depth. Okay. Hit OK. So we should see this tool comes perfectly down and cuts that chamfer perfectly. Beautiful. Okay. Let's do our drill and tap. So we're going to copy. Let's do select the two of them, two check marks, copy, Control V. I always forget that. Weird. We're going to go in and we're going to change our plane right off the bat to G56. Copy that across. We can then go into our linking parameters and our depth on this hole. We can talk about that. So for this hole, if we look at our drawing, we need 1/2 an inch of threads. So let's go open up our OneNote. So this time we need 1/2 inch of threads. So we'll add 50 thou for our piece. So that will be 0.55. So let's go to a depth of something like 0.625 for our drill. And again, we've kind of already accounted for tip comp and all that stuff. So, and then lastly, I need to go to change a tool. I'm going to select a tool. We got to figure out what drill we need to use. So let's find our drill tap chart. For a 1/4-20 hole is a 5.8 millimeter. If we look up our 5.8 millimeter drill, that has an equivalent of 0.228. I already know this one. It's a number 1 drill. I use a lot of 1/4-20 roll taps. Number 1, you start to remember all the numbers after a while. 0.228. Filter for a drill equal to 0.22. Enter. Number 1 drill. Hit OK. This is going to be tool number 6. Finish. I'm going to slow this a little bit down, and I'll put this to 0.00228. It gets me 27 inches per minute. And I'll go to my cut parameters and change this also to update it to the new drill size. Everything else should be the same, except I haven't selected my geometry yet. So I'm going to delete these guys out and select these holes, hit OK, and we'll regenerate that. Can look at how deep we're going based off our threads, not interfering with anything bad. It's good. So again, remember, if they ask for a drawing, 1/2 inch of threads, that's what they expect, 1/2 inch of threads. You have to push your drill past it. They're expecting that. Okay, they're expecting you to drill past a little bit more. I hear lots of complaints from companies that people do not ever tap the holes deep enough. So it's a good tactic to know. Let's do our tap right off the bat. Let's change our planes to G56. Let's go to our tool. Let's select a library tool, filter, get rid of our equal to. We will choose right hand tap, and let's get rid of drills. Let's find our 1/4-20. Spindle speed, again, 1000 is going to work well for us. It'll automatically select your feed rate. Linking parameters, we're going to change this depth to 0.55, which is what we calculated out. And that should be good. We'll just change our geometry. This. There we go. We can regenerate that. And we can take a look to make sure that we are drilling deeper than we're tapping, and it looks like we're getting about the proper amount of threads because again, when this tap comes down, we'll have a little area where there might be no threads. Look at how much bigger the tap is than the hole that it looked like, right? So that's why it's important to know that the holes that MasterCAM shows you are not always correct. Okay, we now have to get some holes here. Now, this is going to be interesting. Looking at my drawing, we need a tolerance of -0 and +2 thou. A regular drill hitting a +2 thou tolerance is pretty tight, especially if you're going for a 0.2495. When I see 0.2495 and a tight tolerance like this, that screams to me, reamer. Okay, hence the general note, ream to suit. That will mean that we got to ream this hole, and we're reaming this hole because it has a mating part, which is a dowel pin that's going to get pressed in. Anytime you have a dowel pin that has a press or a really nice sliding fit, you're going to want to ream the hole to get a really nice finish. So see how the hole is slightly undersized? That should allow for a 1/2 or a 1/4 inch dowel pin to slide nicely in and be press fit in nicely. So that being said, when we ream a hole, the process is as follows: spot drill, and then ream. Just 1 second, I have a crying dog behind me. I gotta let her down off the bed. Little break of the action. Awesome. Okay. We drill a hole. So we're gonna spot drill. We're gonna drill a hole. But we're gonna leave a little material from where actually, so we'll make this blue. The material that the drill leaves, or like the actual hole size. So we drill out to a smaller hole, and then we ream to the blue diameter. Now, the question is, what drill size should we use? Well, your drill should leave 3% of material for your reamer. Reamers like that 3%. Any less than that, and the reamer is going to kind of like not have enough material to grab into. It's just going to kind of push the material, not cut it, or rub it. Any more than that, and we could risk breaking the reamer. So if you recall, we have a 0.2495 reamer. And if I take out my calculator, 0.2495 times 0.97, because that's 97%, which is what the drill size is. So the drill size should be 97% of your hole diameter. I'm getting 0.2420. We're going to go to see my chart. 0.2420 is a letter C drill. So we're going to use a C drill. I am going to now, first off, do my counterbore. So I'm going to copy and paste this first one here with my 3/8 spot drill. Actually, I'm going to first update the hole. My depth, well, the diameter. Wait, did I already? Oh, I already did this. Why am I doing spot drill? I already did the spot drill. I'm silly. I just go straight to my drill. Okay, let's drill a hole. So let's select our tool. Let's change this tap, by the way. I didn't change the number of this tap, so let's change this to 7. Finish. Select library tool. filter for a drill equal to 0.242. Yep. This will be tool number 8. My drill could be about 6,000. That's good. We'll do chip break, even though I don't know if it needs it. We'll see when we get to the depth here. Depth will go to the bottom of this hole. 0.188. Yeah, we don't need we actually could just do this all in one pop. So just do regular chip break or drill counterbore. And what we'll do is we will do tip comp, and let's add. We need to make sure there's a little bit of air, because when you press in a dowel pin, it compresses the air inside of the hole. So we need to make sure there's a little bit of material there for that. But the bottom of our drill will tend to give us that, the angle. So by giving a tip comp and by giving it like, yeah, we don't want to go too much or else the dowel pin will press in too much. So 10,000 is probably going to be good for us there. Let's see, that goes a bit past, okay. Because again, we're shooting for a full reamed hole all the way up to this point. That's looking good. And we'll copy this and paste this. Such a little part, but all these different tool paths really add up, doesn't it? 1 inch. Okay, so let's go back to the top. Let's select a new tool and let's filter and get rid of this and select a reamer. There is no reamer because we have an equal to. Let's see if we ignore. We probably won't have the correct size. We could do a 1/4 inch reamer, but technically that's not the size of reamer we're using. So let's just make our own. .2495 is the reamer I believe I have in my shop. Okay, this is fine. This is fine. The chamfer distance, that's about right. And this is just 0.2495 anyways. Just equal like that. The cutting length is probably a bit longer, at like 2 inches or so, technically. And then the tool is good. There is a general rule for reamers. That is that when you're running a reamer, your reamer speed and feed, it should be about 1/2 the speed and about 2 to 3 times your feed. So whatever your drill was, you want about the half about the speed and about 2 to 3 times the feed. You want to push that reamer a bit harder. It's not cutting that much material. It only has like 7 thou of material to cut. So there's not much here, guys. Let's go back to MasterCAM. Let's do half the spindle, 3,000. Let's bump this up to, let's say 60. That's not, I don't probably want to go more than 60. 60 is probably good. So let's do 2 times. That should work well. We could, honestly, guys, first time I've reamed holes in MasterCAM, so I might change some stuff up later. One thing with this drill counterbore is when it drills and then it rapids out, but it's best for the reamer to keep rotating and feed back out. So that's not what I want. It doesn't look like I have an option. I'm trying to think. Maybe we don't get to. I thought we'd have an option here. In mine, we used to have it. We want a G85, not G81. I might change this for later, but for now we'll just use drill counterbore. But I might explore these options a little bit to see if I can figure out how to get my G85 in there. Linking parameters, our depth is actually just going to be 0.188, but we're not going to turn on tip comp. Coolant definitely on. So you just see that this is going to come in. A reamer, the side of the tool does not cut, it's just the bottom. The sides are just more to help keep it aligned and stop it from rotating, and it will give you a beautiful finish. And I don't believe there's this big chamfer on there. If there is, we can try to push it a bit further, but well, there is a chamfer on it on the reamer tool. I just don't know if it's that big. It might be, actually might be right. That's okay. No matter what, I know what the dial pin looks like, and it should fit in that hole. Regardless. Okay. Am I missing anything? When you have parts like this, you forget some things, but I think that might be it. We can create one last stock model to show us what our stock looks like at the end if we really want to. Looking good. So let's select our entire program. Let's go verify, and let's see in our simulation if we notice anything wrong. Whoa, it's fast. And we can turn on our workpiece. And we're looking for these blue shiny lines. Blue shiny lines mean your stock and your part are being at the same exact plane. Now, you won't get blue shiny lines inside your holes because, again, the holes were never the proper size to begin with in MasterCAM. So don't worry about that. You just got to trust your brain. But everything else, looking smoking. Beautiful, guys. Looks like our cut time is about 2.5 minutes. Total time 2.5 minutes. That's pretty dang good. Might be a bit longer. A lot of tools set up, so it'll be a challenge for us to try to get this all done. I'll try to have some stuff ready though for us, ready to go, so you guys can see the process of all three. Let's see if we can get everyone's cut. Now, you know the rules. Before we move on, we do have to tell ourselves how to set up this program now. Okay. So let's get a setup sheet opened up. Let me just open up this. Just the one, yep. And we got to fill this out. Company. Part name. Left hand. In fact, we can say ENG-001, like capitals for that. We need one per assembly. So technically your group might want to fill this job sheet out with specifically, like if there's 5 people in your group, you should put quantity 5. I'll have some of these for you to fill out in class if you want. You could write your name in here. Our stock material, if you want to recap what that was, we can. If I believe correctly, we are using 1 inch by 2 inch material, cut to 2.5 inches, 2.625. Let's double check. We could turn on our stock. We could do analyze entity. 2.5. Material is 6061 aluminum. And the quantity needed is 1 per part. Again, you could fill out exactly how many you want. Sometimes if, let's say, a customer ordered, trying to think why I have 2 quantities anyways, stock. Oh, sometimes you cut, like, you might cut 1 bar that actually cuts 3 parts, let's say. It's weird, but don't worry about that. Normally for users, it'll just be the same. Okay. I'm going to start talking about my op1 just while my mind is fresh on the subject. Op1, this is going to be let's say align part to left side of left vice jaw. 2.5 inches should be along X axis, 1 inch Y axis, and 2 inch Z axis. This just tells a person how to actually rotate the stock in the vise. Nice thing to put in there sometimes. Okay, I'll come back to that. And I'm just saying that just as a little help for my guy, but I also will put that here. But let's start with our tools. So let's let me drag this guy right here. Choose this, and for me to fill out my tools, I just like to open up one of my tool paths. You want to make sure before you close the tool path that it's still selected that tool. Tool number 1. I have 2, and I'm just gonna be lazy and do this. 7, 8, 9. Description is 1.5 inch face mill, FM. I have a 3/8 spot drill. Nothing special about these tools so far. Number 16. And sometimes I like to put number 16 and then also put the decimal just so they have both instead of having to look up a drill decimal equivalent chart. Make sure to specify roll tap. Tool number 5 is 3/8 end mill. Now there might be something special. We want 0.75 inch flute minimum. We can just do the length of the holder. Does that matter? We're going down how deep in our part. Again, I'll enter this value if I think that there is a chance that the tool holder could crash into our part, but well, we cut down to the deepest point of our program is minus 1.4. Yeah, we might want to 1.5 inches out of the holder, because if we don't have enough tool out of the holder, we won't be able to cut down to that depth. So definitely let's add that in. So this is what LOH stands for. It just tells them the length of the holder minimum that it should be. It could be a bit more, just can't be any less. So that'll at least give us 10th of clearance. So that will just mean that when our tool goes down to cut our part, we will make sure that when they put it in there by saying it has to be at least 1 point, whatever it was, 5 minimum, there's still going to be a gap between our holders, so that doesn't just crash in there. Every other tool that I use, I could tell based on the way that the tool works, it's not going that deep, so there's really no issue. There's no way that it's going to crash. So if you think there's a chance, you might as well put it. But if there's no chance, then you don't have to put it, because then you're just making them do too much when they're setting up their tools. This is my contour. Okay, so tool 5. Tool 6 is a number 1 drill. Number 1 drills are 0.228, if I remember. Just look at my MasterCAM program. Number 7 is a 1/4-20 roll tap. Tool 8 is a C, or 0.242 inch drill. We might run out of holders. I never thought of this. Huh. Face mail spot drill. Oof. Well, hopefully that other part doesn't mean 2. Ooh, I don't know, man. We might be pushing it. We'll make it work. It's fine. A chucking reamer is a reamer that is meant to be put into a chuck, which means you're typically using a machine. So maybe I'll just put a C dot reamer. No. We don't want to use a hand reamer in the machine. We want to use a chucking reamer, which is meant to be on a CNC machine. That's good. Okay, op2 offsets. Ooh, we also need op3 offsets. So we should also change this up a little bit. Let me fix this. Let me do, let's do, open this up first for me, unmerge this. That has all that stuff in there. Copy, paste down here. Copy, paste down here. Delete, unmerge. Take you guys, and we'll copy that down one. And we'll change this to op3 because we have 3 ops. It's a modular setup sheet. There we go. All our tools are good. Op1 offsets. We know that op1 is going to be touched off. The probe is going to be touched off the left side of the part. Or stock, I should just say. We just say left stock. Back stock. You could write it however you want. And when we touch it, it actually is going to be at 0 already. We notice how we didn't move it like Titans did. Top stock. And let's just format painter this. When we do touch our Z though, we will be moving it down 20 thou, if you remember that our Z has 20 thou stock on top of it. Op2, we flipped our part. Our position is actually going to be left side of jaw, left side fixed jaw. I'll just put F. This is going to be our Y0 is going to be our fixed jaw. What do we call it? We could just say left fixed jaw, front of fixed jaw. And our position on this one is going to be top of parallels. After we touch X0 as our left jaw, we'll bump our part up to it, which is where our X0 is. So our 0 will be there. Our Y0 will also be there. But our Z, because it's going to be at the, when we set it, we're going to set it off the top of our parallels. Why do we choose the top of the parallels? Because parallels are machine features. That's the best machine feature we have in the machine, other than the vise itself. But since our part is sitting on it, they're machined. So we can measure off the bottom. And then to get our, we want our Z0 to be in the top of our part. So all we got to do after we figure out where the bottom is just offset our Z up the thickness of our part, which makes it very easy. So we got to just take a look at what size our part is in that dimension. So after we touch off of, we flip it around, the bottom, exactly where this is going to be on top of the parallel. So we're just going to move it up 1.4 inches. And that will set our Z0 to be where the top of our part will be. And our part should come out exactly at 1.4 inches. Op3 offsets are easier. Op3 offsets, because our stock is no longer in our way, we have a very easy job at setting it. Now, I believe in op3, we are just going to be flipping it like this towards us. So it is going to be left part, left side part. Notice I'm saying part now and not stock. And we could say back part. And our Z0 will be our top of part. Now you might want more room sometimes to specify a little bit more about what you're talking about, but the Z0 will just be the top. There's no stock there, so we can just simply touch the top face because it's been machined in op1. It is a machined surface. We can use that now to set our 0. So 0. Oh, whoops, I meant to put all this stuff here. 0, 0, 0. Okay, I imagine I have a dream that we will go and let's see, op2. I got to tell them how to flip the part. Whoops. .180 degrees, I could just say upside down. Ensure. Now I'm going to take a look at my part. I believe the radiuses faced away from us. So ensure that the radiuses face the back of the machine. You could say that, or you could say that the flat faces towards you. I might say the radius because it makes more sense. So op1 will be on the left. Op2 could be we could do everyone's op1 to start. And then we do op2 and op3 together. That'd be fun. So and sometimes it's nice to give pictures about what it would look like as well. And 10-32 holes face toward you. In right vice. Then op2 and 3 together. I'll show you guys how we can run 2 different programs or 2 different like ops at once in our machine. I think that's a pretty good description for our operator. You want to make things nice and simple for him, right, guys? Just gonna make this nice, outside border. And then lastly, we enter some tolerances that we want to make sure that we hit. So let's look at our PDF. So we'll start with our 0.9375 thickness. I'm going to do for my painter. What? Okay, whatever. I'll change it as we go. Whatever. I'll do this. Tolerance range for this one is going to be just general. It's to 4 decimal places, but we'll go down to 3. So just PM plus or minus, I'm going to say 0.01. Then our next one we'll do is our, let's just say 0.5 depth. Doesn't really matter what order you do. I'll do depth because D sometimes I say is diameter. That is also, or that one, our depth. Ooh, actually, I should be changing these. That's one thing I forgot. We'll make our trailing zeros on, and we'll put it to 3,000. Close. Same with U. That's the only one I got to change. Everything, I pretty much want to have tight tolerances. Trading zeros and 3. Okay, 0.5 depth. That's going to be also plus or minus 0.01. Our 1.5 thickness. .375, what do I call that? Width, I could just say. Same thing, plus or minus 0.1. Width or whatever, overall length, whatever. That's the same. Because again, these don't have dimensions, so I refer to these tolerances at the bottom. I think that's all of those. Taps I don't have to worry about. I could just use a thread to make sure that they go deep enough. Actually, we will say 0.375 tap depth. What the heck? I won't really put a tolerance there. We just want to make sure we have a minimum. I'll just say min. The same min 0.5. We'll say 0.5. I could also specify the specific tap or thread that's being used, but okay. Then lastly, we're going to do the 0.2495 reamed hole, or I'll just say bore. I'll just say hole. This tolerance is plus 0.002 minus 0. Now you guys and you guys should have, I'm just being picky at this point, but regular borders. And same thing, we'll just draw in like that. Perfect, beautiful. I think that's it. And if we follow that and we check all those tolerances, we should have a good part to make. Now, obviously there's more tolerances on this part, but let's say the customer only really cared about these ones. So I'm just going to pick off, we don't want to measure too many, but in reality, we'd want to make sure that everything matches up with the drawings, because again, you're signing your name that you certify you made it to their specifications. So we have our program. I'm going to save this so we have it ready for our class. Save as ENG-001 job sheet. And then we'll make sure I'll go to my program and I'll save this. I believe it should already be saved. I'm going to save it how I always want you guys to save yours. I'm going to select all this stuff, but I'm going to deselect my stock models. I'm going to deselect my stock. Let's go to my isometric view. Voila, there's our part. Let's save it. There we go, guys. There's our part. This will be a fun one to make. Be fast. It will try to make it nice and quick. We'll see if we get it done in 2 hours. It will be a major task. But there you go. There's programming part with multiple sides. I hope you guys have fun with that. I hope you guys learned a couple things. You can see just a simple, small little part like this especially when it has a bunch of holes, can actually lead to a lot of different tool paths being used. So we'll leave it there, guys. I will see you in your next part. Cheers for now.